Before we get into full-blown drainage design problems, let's take a look at a couple of the parts and pieces of what we've been talking about and how that all comes together. So let's say that I have a catch basin, and the reason it's a catch basin is I want water to be able to come into it. That'd be a side view. And just so you understand, the soil level would be, that's our road, something like that. So let's say we have water going into that, and that water volume is defined as Q. That would be based on a storm drainage area, for this example, of 1.8 acres. For that area, we have a time of concentration equal to 20 minutes. And we have a runoff coefficient for the area of 0.6. So it's more of an urban environment, a lot of sidewalks, a lot of rooftops, not so much landscaping. So based on that, how much water is going into the catch basin? Q is equal to CIA. Q will be equal to 0.6 times our intensity. I is equal to 120 over T plus 20. So I would be equal to 120 over 20 plus 20, or 120 over 40. 120 divide 40. That would be 3 inches per hour. So 0.6 times 3 inches per hour times 1.8 acres. And if we keep units of inches per hour and acres, we get units of cubic feet per second, or CFS, in the end. So 0.6 times 3 times 1.8. That's 3.24 CFS. So now we're going to design a pipe that can handle 3.24 cubic feet per second. Here's where you have to become the designer. You have to think about what are all the different options you have. First of all, we want V to be between 2 feet per second up to 8 feet per second. And we'll talk about that 10-foot that Brookhaven does a little bit later, but keep our velocity between 2 and 8. We also have diameters we want to work with. We want to keep between, say, 15 inches all the way up to 120 inches. Now again, we're not going to use a 12-inch diameter because we don't want anything getting clogged in there, so let's stick to 15 inches. As long as we make sure the water flows at a certain speed, we can figure out certain size pipes to work with. The hardest part about this is, where do you start? Do you choose it by pipe size, or do you choose it by velocity? It's going to depend. For this example, we're going to choose it based on velocity. Let's say that I want to keep, what kind of K is that? Jumps around a little bit. There we go. We want to keep velocity equal to 5 feet per second. And when I say equals, it doesn't have to be exactly at 5. It can float a little bit higher or a little bit lower. We want to keep it around there. Well, if we're trying to keep the velocity at a certain rate, we have two equations to work with. We have Manning's equation, V is equal to 1.486, R to the 2/3, S to the 1/2 over N. For that, we need to know what diameter pipe, that'll be our radius. We need to know the slope of the pipe as well, which we don't have that information right now. And we'd also need to know what type of pipe it is for the roughness coefficient, because N varies depending on the type of pipe. So this would not be the best choice of a equation to use right now. We also have an equation, Q is equal to area times velocity. So for that one, that would be our best choice, just with the parameters we have. We have a Q equal to 3.24 CFS. That'll equal to the cross-sectional area of the pipe, which we're going to determine, times a velocity, and we want to keep it at 5 feet per second. So let's see what we get for A. A would be equal to, we divide both sides by 5, divide by 5, 3.24 over 5. So that's a 0.648 square foot area. Okay, so what do we do with that square foot area? We have to figure out what the diameter is going to be. So how do you figure out the diameter of a circle? Area is equal to pi d squared over 4. So get used to this one, because you're going to be doing this equation quite a lot. 0.648 that's our square foot measurement, is equal to pi d squared over 4. So d will be equal to the square root of 0.648 times 4 over pi. And you know what? I should have shown the cancellation. Let me do that. 4 over pi, 4 over pi. And that cancels. To get rid of the square, we square root both sides as such. So what does that give us? Times 4, divide pi, and that would be square rooted. So my diameter is equal to, back to blue, 0.91 feet. That's our answer. But they don't make pipes that are 0.91 feet. They do make a pipe that is equal to 1.0 feet. That would be equal to 12 inches, but we really don't want to use that. We'd like it to go up to 15 inches. So in that case, diameter would be a 15-inch pipe, 15-inch diameter. But that's going to cause all sorts of problems for us. If we go to a 15-inch diameter pipe, Q equals AV. This equation no longer works where if we say 3.24 CFS is equal to 1.25 squared pi over 4, that's our area, times a velocity of 5 feet per second. So 1.25 times pi divided by 4 times 5. 3.24 CFS does not equal 6.14 CFS. Okay, so when you do the math, it doesn't equal, which means we got to make some changes on this. So what do we change? We can either change the Q, we could change the velocity, but you really can't change the area quite so much. Okay, because the area of the pipe is fixed at 15 inches, which means if I want to keep the velocity at 5 feet per second, then my flow rate Q is going to go up. And if I want my flow rate to stay at 3.24 CFS, then my velocity is going to have to go down. So let's look at both examples of this and see which way it would work. Let's say that I want my Q, let's hold Q at 3.24 CFS. All right, holding that, we would say 3.24 CFS is equal to 1.25 squared pi over 4, because we're going to use that 15-inch diameter pipe, times V. That's my dog. So velocity would be 3.24 CFS, but 25 squared pi over 4. And that would be, let's see, 1.25. That would give me a velocity of 2.6 feet per second. Is that between 2 and 8 feet per second? Yes, so that is a good option. Or, that's one option. The other option is to hold V at 5 feet per second. And if we do that, then that equation becomes Q equals AV. Q would be equal to 1.25 squared pi over 4 times 5 feet per second. Q would be equal to, let's see, 1.25 times 1.25 times pi divided by 4 times 5, 6.13 CFS. So what that's telling us is the pipe could actually handle more water than is actually going in. We're only putting in 3.24 CFS, cubic feet per second, but the pipe could handle as much as 6.13 cubic feet per second. Not a bad thing, but it's something you have to keep in mind for down the road. So this gives you a quick idea of the Q equals AV formula and how we can use that in different ways to, I'll take it in a second. I'll show you in different ways of solving that problem. So let's take a look at another one in a second. Let me take the dog out first, then we'll take a look at another problem. All right, the dog didn't have to go out. He was hungry, so he's got his dinner, so I can get back to work. Let's look at another example now. Let's use something with the Manning equation. 1.486 r to the 2/3 s to the 1/2 over n. So let's figure out what's the velocity of the water flowing through a pipe. Let's say that we're going to deal with a 24-inch diameter pipe. Let's say the slope of the pipe was equal to, let's see, 0.005 feet per foot. Okay, this would be equivalent to 0.5%. Slope always has to be in feet per foot for these calculations. And let's say that we're using a pipe that has a roughness coefficient of 0.13. So let's see how that all works. First of all, we have to get our hydraulic radius. Hydraulic radius is taken as d over 4. That's our diameter. Diameter is always specified in inches, but calculations have to be done in units of feet. So that will be 2 feet over 4. So my hydraulic radius is 1/2 or 0.5, whatever you rather see on there. Now we can plug our numbers in. V is equal to 1.486 times 1/2 raised to the 2/3 power times s 0.005 raised to the 1/2 power, all of that over 0.013. Now this one's really important for you to get your calculators out, if you hopefully have them out already, and do this math with me, because if you're not able to put this into the calculator, unfortunately I'm not there to see the keystrokes you're putting in and help you out. But what I'm going to tell you to do is get these terms done first. Okay, the way I put it in is I put into my calculator as my hydraulic radius, so 1/2 equals, and I use that equal sign quite a bit, raised to the 2/3, and the 2/3 has to be in parentheses, times slope to the 1/2. The 1/2 power is a square root, so I multiply that by the square root of 0.005 times 1.486 equals, divide 0.013. And I get a velocity equal to 5.09 feet per second. Now, if you didn't get 5 feet per second, 5.09 feet per second, pause the video, go back and redo the math. Make sure you do 1/2 equals, raise that to the parentheses 2/3 power equals, times square root of 0.005 equals, times 1.486 equals, divide 0.013 equals. It takes a lot of steps to get it right. And if you still can't get it, email me. We'll do a Zoom session real quick. It's really critical you get these calculations to work right away. So please, if you're not sure on that, give me an email and we'll set it up real quick. That's my velocity. What's nice about this, or one of the things you'll find as a designer, is if you choose your diameter and you say that's the diameter I want to work with, and you let everything else kind of float up and down, the slope changes, the speed changes, it makes your life a little bit simpler. Let's try another example. Let's say I want the velocity of the water to be 4 feet per second. And I'm going to deal with a diameter pipe that's equal to 36 inches. N for that pipe is 0.015. Find the slope. And we're going to find the slope in feet per foot. We're not going to start changing it to percent grade just yet. So let's see what our equation turns out to be. V is equal to 1.486, r to the 2/3, s to the 1/2 over n. So I'm solving for slope. So what I'm going to do right away is I'm going to bring all my terms over to the other side. And this way, that cancels with that cancels with that, and that. And I'm left with an equation of s to the 1/2 is equal to Vn over 1.486 r to the 2/3. How do I clear the s to the 1/2? I heard someone say it. A little bit louder. Good. Square it. Square both sides. So my slope is equal to Vn over 1.486 r to the 2/3, and all of that will be squared. Really good equation to work with when you're finding slope. So to find my slope, I plug it in. The velocity I'm looking for is 4 feet per second. The n value is 0.15, that's my roughness coefficient, divided by 1.486 times r. I didn't do my hydraulic radius, I'm going to do that now. R is d over 4. So what's that equal to? If you're saying 3/4, you are correct, because you have to take the 36 inches and make that into 3 feet. So 0.75, or 3/4, raised to the 2/3. Okay. Oh, squared. So let's see, 0.75 raised to the parentheses 2/3 times 1.486. Flip that over, times 4 times 0.015 squared. 0.0024. And usually for slope, we take it out to 4 decimal places, because when you turn that into a percentage, we lose a couple decimal places. That's our slope. It's important when you're doing these numbers, don't round a lot. Don't do a calculation, write it down, and then try and put it back in your calculator. It's really important to be able to run these numbers all the way through. As you get further into this, you can do a lot of these equations on Excel, so you can set up your own spreadsheets where you can just plug your numbers in. It'll do the calculations for you as well. All right, so that is our slope. Now let's add one layer onto this same problem we did. How much water will that pipe convey or allow it to flow? All right, so if I wanted to find out how much water flows in this pipe, what do you think? Hopefully you were thinking Q equals AV. And that would be the perfect way of solving for it. Q is equal to area, and this is a 3-foot diameter pipe, 3 squared pi over 4, times my velocity. We set our velocity at 4. So my Q will be 3 squared times pi times 4 divided by 4. This pipe will handle 28.27 cubic feet per second. That's a lot of water. That's coming out through a 3-foot diameter slug of water coming out. It would just massive volumes. So that's how much that water can handle. In reality, how much this is ever going to see? Probably half that, if you're lucky. Okay, they really are never going to flow as full as we want them to. All right, so hopefully that's explaining how we get certain parameters using those equations. But we have a lot of practice problems to go through together. This way we make sure you understand it really, really well. So let me pause the video here, get set up for our next setup, and we're going to do a race on the math. All right, so I got a little challenge going on. We're going to race to the finish on this one, see who gets it first. So, 2 problems. If I give you, let's see, a 48-inch diameter pipe and I want the velocity to be at 5 feet per second, and an n is equal to 0.013. I want you to find the slope and find what the flow rate Q is going to be. And when you're done with that one, I'm going to give you a 24-inch diameter pipe with a slope equal to 0.006 feet per foot. I want you to find the velocity and Q. Okay? So pause it now, see how quickly you can get these things calculated, and then I'll show you how I get mine calculated. All right, pause it and come back when you're ready. Okay, I got my solution. I got my slope to be around 0.002 and a Q of 54 for the first one, and a velocity of 5.55 feet per second and a Q of about 17 CFS. And it actually took me just as long as, I didn't pause the video at all, it took me that long to figure it out. Let me show you how we did this, okay? Now, if you're moaning and groaning and saying I cheated, I didn't cheat. I did nomograph, okay? And you have a nomograph now too. If you remember from time of concentration, we can use nomographs to graphically solve equations. And this is a perfectly valid way of solving that Manning equation. However, you do have to do the math afterwards to double check because it's close but not perfect. Like your numbers are probably not exactly what I gave you before. Let's check this first one. So a 48-inch diameter pipe, and it's kind of hard to read. That's 42, that's 48, that's 54. So 54 inches, and what do we have? A velocity of 5 and an n of 0.013. You know, before I show you this, I should show you what's on this nomograph. That would make more sense. So on this nomograph, your first column is Q. Your second column is your diameter. And this is actually the true size diameter of the pipe, not a hydraulic radius or anything like that. So you just plug in what your diameter is in inches. This third column gives you the two most common roughness coefficients. And actually, it's the only two roughness coefficients that we're going to be using. 0.013 is on the right side, 0.015 is on the left side. So depending on what number you're looking for, you choose the left side numbers or the right side numbers. I do want to make sure you be very, very careful. If you zoom in really close on this, it's a decimal point. It's 0.0200, 0.0300. So all those numbers start with a decimal point. Just keep that in mind. And the last column is our velocity. So let's see what we got. We said, so 0.013, I'm using this side, the right side number. So 48 and 5. 48 and 5. I'm going to play with this a little bit. There's 5. And here's 48. Now, the way I would do this normally is I'd have a straight edge, an engineer scale, no architectural scales, but an engineer scale. And I'd be lining these up pretty much dead on. It's amazing how accurate these things can be. Okay, so based on that, if I zoom in on there, there's my 0.0020 for my slope, and my CFS 50, 60, sorry, 60 CFS, not 54. I got it too quickly, so that should be around 60. We'll just change it. First mistake of the semester, not too bad. Okay, so about 60 CFS. I will go through the math on that in just a moment to show you how it is. But I do want to show this nomograph first. On the second problem, 24 inches and 0.06, And on this one, I should have told you n is equal to 0.015. At least it'll work in the video. You might be yelling at me through the at the computer right now because I didn't tell you that before, but I can't hear you, so it's okay. Let's see, 24 inches and 0.0006. I'm sorry, n of 0.013. I wish I could just edit out what I just said. Oh, gotta stretch that. 24 inches, 0.006. That looks pretty close. Okay, so in that case, my velocity, 5.2, 5.4. V is 5.4 feet per second. And my Q would be around 20, 10, 11, 12, 13, 14, 15, 16 and a half. Okay. Somewhere in there. All right, let's see how I get those. So the nomograph is just taking a straight edge and running it across and drawing a line on there. I do have it set up as a single PDF, so you can print out multiple copies. You don't have to do it on a computer screen. And hopefully before I post this tomorrow morning, or post this as you're watching it, you'll have a cleaner copy of what's there. It's actually not a very easy nomograph to find online. Okay, so let's go through the actual math on this and show you how it's done the math way, the fun way. We'll do that first one. So first one we had Q is, nope, not Q, looking for Q. Our diameter is 48 inches. Velocity is 5 feet per second. Okay. So on this one, we have a couple equations. We have Q is equal to AV, and V is equal to 1.486 R to the 2/3, S to the 1/2 over N. So what we can do is let's solve for the slope first. V is equal to 1, I already have that. I want to rewrite it one more time. Let's solve for slope. So if we bring everything to the other side, S to the 1/2 is equal to Vn over 1.486 R to the 2/3. And if you need to see how I cancel that out, go back a little ways in the video, and I showed you that cancellation before. You can rewatch it again. I don't want to just do it again now because I don't want to keep these videos any longer than they already are. I'm going to square both sides. So that's going to give me slope is equal to Vn over 1.486 R to the 2/3 squared. So my slope will be equal to 5 times 0.013, 1.486 times R to the 2/3. So my diameter is 48 inches. Oh, this is my favorite pipe. Okay, 48 inches because hydraulic radius of a 4-foot pipe is 1, and 1 to the 2/3 is still 1. So it makes it nice and easy. I'll show you to the 2/3. And all of that will be squared. So 5 times 0.013 divided 1.486, and I square that. Slope is 0.0019. What did I come up with on the nomograph? 002. I'd say that's pretty close. I would give myself 100 for that. Okay, so that's my slope, and that is in feet per foot. We're always going to be working in feet per foot. It's not very often you'll see percent. If it is, I will call it out, and I'll make sure you notice that there's percent sign on there. So we also have to find what our Q is. Whoa, screen moved on me. So Q Q is equal to AV. Now, we're not going to go through this whole process, but I want to show you what we could do. If you were bored, you could take V and plug that in, 1.486 R to the 2/3 S to the 1/2 over N. Now that's a cool equation. We already have velocity, so we don't have to do that. We also have A, so that will be 4 squared pi over 4 times our velocity, which is 5 feet per second. So that gives me a Q equal to 4 squared times pi divided by 4 times 5, or 62.83 CFS. Now on the nomograph I came up with 60, a little bit more. I'll give myself a 95 for that. All right, so it's close, but it's not going to be perfect. If you're using a scale, you can really get those numbers in a lot closer. There's no way I'm estimating to 0.83 though. I might have said 61 or 64. I wouldn't get it, that close. So what the nomograph's great for is getting you a rough idea to see if you're in a ballpark. And I'll show you how we can pick out pipe sizes for the next class. We're not going to do any more after this one today. How we can use the nomograph to pick out sizes very quickly and then back it up with the calculations as well. Okay, I still got to finish up one more by hand. So that's going to be slope of 006, N of 013, and 24. So diameter, how are we looking for diameter? Velocity, we have diameter is 20. I don't have to scribble, I can erase. Diameter is 24, slope is 0.006, and is 0.013. So I got to find my velocity. V is equal to 1.486 R to the 2/3 S to the 1/2 over N. You do not have to memorize this formula, but I'm going to say it so many times it's going to get stuck in your head. So V is equal to 1.486 times R. R is equal to D over 4. So that'll be 2 over 4. That's 1/2 to the 2/3 times 0.006 to the 1/2 over 0.013. So let's see how I do. 0.5 raised to the 2/3 times the square root of 0.006 times 1.486 divide 0.013, 5.57 feet per second. And on the graph, I came up with 5.55, so I'd give myself like 110 on that one, bonus points. And Q, we always finish out going back to Q because we want to find out what the pipe really can handle. Q is equal to AV. So Q is equal to 2 squared pi over 4. This is also a nice size pipe because that cancels, times 5.57. So 5.57 times pi, 17.4 CFS. What did I come up with on the nomograph? Well, I wrote a lot on this one. Wow. 17 CFS. You know what? We did such a good job today, we can call it quits. So have a good night. Wednesday or Thursday, depending on when you're watching this video, we're going to spend that class going through more example problems, and then we'll have some homework over the weekend. So have a good night, and any questions, please give me a shout.